Thank you for coming, everybody. We are delighted today to have Professor Pedro Ferreira delivering our colloquium. Pedro is a cosmologist. Actually, we're welcoming him back. He was last here 32 years ago in 1993, and we are delighted to have him here. So Pedro is a cosmologist at the University of Oxford, where he's been in one guise or another since around the turn of the millennium. He's now head of the Astrophysics subdepartment and also director of the Beecroft Institute for Particle Astrophysics and Cosmology. Pedro is a recipient of multiple awards, including most recently the Eddington Medal of the Royal Astronomical Society. He's also a prolific mentor of various brilliant graduate students, including a certain Professor Joe Dunkley. And besides the science that we're going to hear about today, Pedro is also a talented expositor of scientific ideas for the public. He's written many articles for Nature, for the BBC, for The Guardian. And in 2014, he actually published a book called The Perfect Theory, which is a wonderful history of general relativity. Pedro to direct his talents in science exposition today towards telling us about his battle against the underdetermination of dark energy. So please welcome Pedro Ferreira.
Well, thank you, Chris, for that incredibly kind introduction. I never gave a talk at the IAS. I gave a small presentation at the Gravity Group meeting down on campus. I was here for an idyllic summer in 1993, and I would go to these Gravity Group meetings with Jim, with David Wilkinson, with the newly tenured David Spergel and Neil Turok, and it was an incredibly formative experience in my life. I hugely enjoyed it. This is work which was done with these three characters, and one of these characters is here, William Wolf. He has really spearheaded this work with me, and he's sitting in the audience. He decided to come and attend this lecture. So if you want to talk about this, you can also talk to him. And I decided to put this plot up because one of the things that would happen in this Gravity Group meeting is Lyman would show up with a new measurement of the cosmic microwave background. And this is what it looked like, 30-odd years ago. On the x-axis, you have the L, which is basically the inverse angular scale. So large angles here, small angles here. And this is the amplitude of fluctuations. And every 6 months, we would get a new data point, which would be one of these big crosses on this plot. And the idea is that you would kind of zoom in and figure out what the universe actually is. This is a plot of the angular power spectrum of the cosmic microwave background. Then it would take 2 to 3 to actually a night to generate each one of these curves. That radically changed after 1995, when Matthias and Uro Seljak figured out how to do this super fast. But that was what it was like, and it was really exciting. We were trying to figure out what was the underlying model of the universe. This is what the model of the universe looks like now. This is the data from the Planck satellite, and this is the angular power spectrum of the cosmic microwave background. And what you see is this remarkable agreement between data and theory. And the theory is general relativity, statistical mechanics, a bit of quantum mechanics, but really basic textbook physics, which allows you to generate these curves and map it onto the data. And the agreement is remarkable. Now, given that you have a mathematical model, which depends on a number of parameters, you can constrain these parameters and you generate these massive tables. And Princeton is notoriously good at generating these tables, very tight constraints on these parameters. And one of the things that stands out is that you measure the existence of something which is driving the accelerated expansion of the universe. And typically we say that this something is a cosmological constant. And for many decades, we've said that it's a cosmological constant. This omega lambda is the fractional energy density in this cosmological constant. And we constrain it to be about 70% of the overall energy density of the universe. And we measure it, this was 2015, at about 52 sigma. So it's just a striking measurement, a very tight constraint on this. Now, it could be a cosmological constant. It could be something else. It could be some form of dark energy. And that is the language that we normally use. We say that there is something out there which is driving the accelerated expansion of the universe, which we call dark energy. Okay? Now, around this time, 30 years ago, we were reaching the apogee of the rise of particle cosmology. And since the 1970s, people had started thinking about cosmology as this tool with which we could learn about fundamental physics. And this is just a selection of books on my bookshelf that I had at the time, which kind of reflect this, that the idea that you would look out on very large scale structure, at very large scales, and it would tell you something about the microphysics. And we all went to conferences on these topics and we read books on this. And there was this very powerful belief that if we could measure the large scale structure of the universe in incredible precision, we would learn something about the microphysical nature of the universe. What does that mean in practice? What does that mean? It means the following. We have a standard model of particle physics, which we call the Standard Model, which incorporates gravity and incorporates all the fundamental forces, and we can write it down, and it's very simple. Some people walk around with this on their T-shirts. And you can write a path integral. It involves quantum mechanics, general relativity. It's very beautiful. On the other hand, we also know, well, the data seems to show that there are these other things around, in particular dark energy. And so there should be something else added to this. And so when we say that we would like to use cosmology to find out what the fundamental nature of the universe is, or fundamental physics, we would like to know what we add to this standard model action, what we add, which will describe all the rest, i.e., what is the microphysics of this something else, like dark energy. So that is kind of the spirit of particle cosmology. The spirit of particle cosmology has been that we will use cosmology, the large-scale structure of the universe, to learn something about what is the fundamental action of the universe. Okay? Now, of course, theorists are endlessly inventive. And in particular, with dark energy, we have seen many hundreds of papers written proposing what this dark energy could be. It could either be the cosmological constant, or it could be something more elaborate, a scalar field or something else. And I just have listed this series of examples of proposals for this dark energy, which I, disparagingly or not, call theoretical sludge, in the sense that it's very difficult to distinguish between any of these theories in practice with cosmological data. And that will be a constant theme in what I will say over the next 50 minutes. So the question you might ask is, people are proposing all these microphysical models of dark energy. Will cosmology actually tell us which of these microphysical models is correct? And this harks back to a paper I stumbled upon about 5 years ago, which was a paper written in the 1950s, and it was a debate between Gerald Withrow and Hermann Bondi. Hermann Bondi, one of the grand men of general relativity, had written a book called Physical Cosmology, where he made a case that cosmology was a physical science and that we should look forward to observations and data, and it will tell us how to understand or constrain mathematical models of the universe which stem from Einstein's theory. And Withrow, being the devil's advocate or not, was saying, well, cosmology had been around then for millennia, and it was always characterized by debates about what was correct or not. And it was very much driven by opinions, people's opinion of what was the correct theory. And that even though there was a mathematical model then, which was Einstein's theory, there were still opinions. It was still plagued by opinions. And in that case, the specific debate that was going on was Bondi and others were promoting a universe which satisfied a four-dimensional symmetry of homogeneous. It was four-dimensionally homogeneous. And the only way to enforce that was to assume that there was some creation, a form of creation of energy which could sustain that space-time. This was the famous steady-state model. On the other side was a theory which assumed homogeneity of three space. But if you did that and you worked out the equations, as Friedman, Lemaitre, and others did, if you wound back the clock, you would have had what Bondi and others disparagingly called a Big Bang. And so the world was not equally, but it was divided between people who thought the steady state was a more elegant proposal for what the universe was like, versus people who thought that the expanding universe was the more elegant proposal. And it was this division in opinions that Gerald Withrow looked at and said, look, this is no different from the kind of debates people were having 1,000 years before about how the universe evolved or was. Of course, this was resolved very rapidly because, for example, with Rees looking at the evolution of radio sources with the discovery of the cosmic microwave background, this was put to bed. And science, in fact, it was a scientific, it showed that physical cosmology was a science, that it could be resolved with data, and you could decide on, it wasn't based on opinions, you could decide which one was the correct theory. But you can ask the same thing about dark energy. Will data be able to tell us what is the correct microphysical theory of dark energy? And that is why I'm giving this talk here and why I've been writing these papers. I want to try and figure out what we can actually say about dark energy. What is the microphysical nature of dark energy? So let's begin with the data, and I will really focus on a subset of data. I will focus on the data which is telling us something about the expansion of the universe. Okay, and you've probably been paying attention to what people have been saying recently, but I'm going to focus on two things. The first thing I'm going to focus on is measurements of the luminosity distance as a function of redshift taken from supernova 1A. Okay, and by measuring light curves and measuring the slope of the light curves and the amplitude, we can get an idea of the absolute magnitude of supernovas at a certain redshift, and we can measure its apparent magnitude, and from the combination of the two, we can measure luminosity distances. So that's with supernova. On the other hand, a tool that has been developed over the last 20 years is that if we map out the large-scale structure of the universe at different redshifts, imprinted in the power spectrum of the large-scale structure of the universe will be vestiges of the photon baryon plasma before recombination. You'll see a set of wiggles, and these wiggles have a fixed physical scale. And so what you have is a measurement of a fixed physical scale as a function of redshift, which allows you to measure the angular diameter distance, and if you measure it along the longitudinal direction, you can measure the Hubble parameter at that time. So you can measure a bunch of things. You measure apparent magnitudes, which are related to the luminosity distance, angular diameter distance, and the expansion rate at a given redshift. So that is your data. And what people have been finding over the last couple of years is that this data is tentatively away from what you might expect if the universe was dominated by a cosmological constant. So for example, from the supernova data, what this shows is the apparent magnitude in which you subtract away what it would be if the universe was dominated by a cosmological constant. And so if it was a cosmological constant, the points would fall on the black line, and what you find is a mild trend going upwards with the most significant point being the point at low redshift. If you look at baryon acoustic oscillations, what I'm plotting here is, again, it's the same thing. You calculate kind of an isotropized measurement of angular diameter distance and the Hubble rate at that point, and you divide by what it would be if it was lambda. It would lie on that line over here, and what you find is that these points are systematically low. Now, we would agree that it's all pretty tentative, okay? So by looking at these plots, it's very difficult to see if it's significant or not. And we will have to look at this more carefully. Now, there is a huge debate on how seriously we should take this data, which I think is a very important part of this exercise. And it would be remiss of me not to mention what are the key aspects of this debate without going into it in detail. The first thing is, if you look at the supernova data and you compare different supernova samples, there seem to be some inconsistencies. And there's been quite a back and forth between, for example, the DES team and people who are not members of the DES team discussing these inconsistencies. And I would say it's still completely unclear whether we should take that seriously or not. And I mean, it's unclear. I'm not taking sides in this. Okay, I'm going to, as George Eustathiou would say, I'm parking it. Another aspect that is brought up is, as you saw, the low Z point plays a very important role. And this low Z point is based on supernova measurements, what we might call legacy supernova measurements, taken quite a while back. And so one is worried that the constraints that are coming from supernova are heavily dependent on this old data set. But again, I'm not worried about that, because in the next few years, really in the next couple of years, two surveys, the ATLAS service and the ZTF, will replenish the data at that redshift. And so we will get a new data set, which we can slide in and see if indeed that point is important or not, or if it's there. Finally, there are some mild inconsistencies between the DESI data set and the SDSS data set. It's small, but it shouldn't really be there. And depending on who you talk to, it's important or not. I should note that. Finally, the cosmic microwave background plays a hugely important role in trying to understand those plots. And I would direct you to the recent ACT paper, where they've done a really thorough analysis of what the role of the CMB in trying to make this inference is. Finally, one has to make assumptions about certain cosmological parameters. And the two notable ones I'd like to highlight, one is that the optical depth, some people have saying that the optical depth, if it was a bit higher, these deviations from lambda would go away. Other people, I think, Matthias Zaldarraga here has pointed out the role of curvature. So all of these are things that one has to take into account. And so I would say that the interpretation of the data in its entirety is still in a state of flux. However, I'm going to assume that the data is correct and is fit for cosmological analysis. And I think that the conclusions that I will come to are sufficiently flabby that you can move around in the conclusions and the conclusions will be correct. Okay, so I've set up the data. Now I'm going to talk about this thing that people talk about when they're talking about evidence for dark energy, which is the equation of state. I call it wology, all right? And it's very important for you to understand what people mean by this, or what people are in practice doing with what they call the equation of state. The thing that you will be shown is a plot that looks like this, with these two parameters, W0 and WA. And a cosmological constant lies at the intercept of those two dashed lines. And the point is that the data is away from that intercept. So this is what is, in the most graphic sense, deviations from a lambda CDM, deviations from a cosmological constant. But let's try and understand where this comes from. What are W0 and WA? Well, what do you do when you are trying to find these two parameters? The first thing you do is that you assume a model for the expansion of the universe. And this is Cosmology 101, the Friedmann equation. You have that A dot over A is equal to, well, you define it as h squared, and is a function of the scale factor, and it has a term which is relativistic matter, omega m is the fractional energy density in matter, and then you have another term over there, which is a function of A, all right? I haven't said anything what this function of A is. We then decide to parameterize this function of A as an exponential of an integral of this thing, where you have this function W of A. And this function WA is a completely free function. Let's call that function the equation of state. All right? So this is the mathematical model of the universe that you use to interpret the data. And this is what goes into inference. Okay? Now, if you are given a model for the expansion rate of the universe, you can calculate those things that we measured, like the apparent magnitude, the angular diameter distance, the isotropized luminosity, the isotropized distance, whatever. And they're all functions of h of A, which are functions of W of A of this equation of state. In other words, these are the things that you measure, but if you have a mathematical model of the universe, you can calculate these things in terms of h of A, and that will give us, you can, given an h of A, you can calculate what these things are for a particular model. So, you now have a model, and you can calculate the observables. You now calculate these observables for a choice of parameters, W0, WA, omega m, H0, and a free function W of A, and then you match it to the data that you've measured with your supernova and your baryon acoustic oscillations, and you estimate what is the best equation of state that fits that data. And if you, for example, assume that that equation of state is just a linear function in A, and you often write it this way, 1 is when this is the scale factor today, you basically have to infer these two parameters, W0, WA. In other words, W0 and WA is simply a very useful way of compressing the data, making an assumption for your universe model. That's all it is. There's no physical meaning to W0, WA. You might want to give it physical meaning, don't. It's just a way of compressing the data. And the crucial thing about this is that this W0 and WA depend on the survey characteristics. They depend on the depth of the survey, the uncertainty at each measurement, where you're putting your redshifts, etc. And they also depend on assumptions about the cosmological parameters. If you remember, that model had omega m and H0. So W0 and WA depend on a lot of things. Let me give you an example. Imagine that your universe was full of something, a dark energy, which had an equation of state which followed this, this black line, okay? Depending on what survey you used, you would get a different linear fit. So for example, if you use the CMB, you'd get a much shallower fit. If you use the baryon acoustic oscillations, you'd get this green line. If you use supernova, you'd get this much steeper line. So depending on the characteristics of the survey that you're using, you would get a different value for W0, WA. So I go back, W0 and WA do not have, it's not useful to think about them as having a physical meaning. They're simply a way of compressing the data, which depends on the survey characteristics. So what do we see? Well, let's go back to what we see. What we see is that we measure a W0 and WA, which deviates from a cosmological constant. If it was a cosmological constant, this thing would be constant, W0 would be equals to -1, and WA would be equal to 0, which is at that intercept up there. But what you actually find is it's somewhere away, so W0 is a bit greater than -1, and WA is less than 0. And we often call these equations, these values of W0, WA, thawing. In other words, that they were more negative in the past and they're growing as they come, as you move forward in time. Okay, so this is what is observed. How do we compare to theory? So, as I said, W0, WA is a way of compressing the data in a useful way. It's just two numbers. It's much better to look at two numbers than a bunch of plots on a line as a function of redshift. How would it compare with theory? Well, this is just stats, statistical inference 101. Imagine that you have a theory which depends on some free fields or some fields. You have to define what your fields are. You have to define the parameters in your action for this field. You have to define the initial conditions. You then turn the handle and you predict what your observables are, your Hubble parameter, your angular diameter distance, your whatever, okay? On the other hand, you have observations. You've gone and spent millions, billions of dollars on observing these things, and you've come up with a data set at certain redshifts with certain uncertainties, with certain covariances. And you put this all together and you compare one with the other in the correct way, and you can infer what the posterior of these observations give you for this theory. In other words, you can find things like confidence intervals, triangle plots, you can work out Bayes factors, and most importantly, you can work out evidence. You can work out whether this data set in any way is favoring this theory relative to another theory, okay? So this is the machinery that you apply to figure out, given a data, whether you should believe a theory or not. But it's sometimes useful to look at it in another way, which is, imagine that you've gone away with your data, and you've calculated a couple of quantities like A and B, and your red ellipse there is what you measured. It's the uncertainty, what you measured, and the uncertainty on what you've measured, and it gives you that ellipse over there. Then you take theory one and you predict what A and B should be, and it lies on that dashed line of, I've got a pointer, I think. It lies over here. And you take another theory and it lies over here. It's pretty clear that this is a good theory and that's a bad theory. I think we'd all agree with that, okay? So let's now do this and replace A and B by W0, WA. Again, W0, WA are just some numbers that you can extract from the data, okay? So you go away and you produce those, the plot that I showed you over here. You've estimated what the W0, WA are for the data, right? Now you get a theory, and how do you find out what the corresponding W0, WA are for that theory? Well, you take a particular choice for that theory, you predict the observables, then given the redshift range and the uncertainties and covariances in that theory, you find what are the best fit W0, WA, and that will give you the priors of W0 and WA for that theory, okay? So you'll have the priors of the W0, WA for that theory, and you'll have the W0, WA that you inferred from the data, and you can see how they compare to each other. Very good. So that was just a kind of a methodological, simple methodological preamble that I wanted to give you. Now, from now on, I will solely focus on single scalar field models for dark energy. And the reason to do this is, one, they're the easiest to work with. They are also the overwhelming majority of the theories that have been proposed. They are also many of the theories that have been proposed that don't involve a single scalar field. You can actually rewrite them in a way that they just involve a single scalar field. So what I'm doing here is you have to pick your arena. I'm picking an arena which I think is quite vast, and so I can make meaningful statements about a vast range of dark energy proposals, okay? And I couldn't not show this. Of course, this was first suggested by Jim and I think his then student Bharat many years ago. And it kind of rediscovered 10 years later by a bunch of us when the supernova data was coming out. And so this is, this is a Princeton construct. And one of the things I'm going to do is I'm going to use the rules of effective field theory. And what is effective field theory? Effective field theory is really common sense fundamental physics. And the idea is that there is a framework that allows you to describe phenomena at a given energy scale without requiring full knowledge of what's going on at other energy scales. And not only that, it gives you a systematic way of constructing what the fundamental action is of that theory at that energy scale. And it tells you how to add in more terms and how they are suppressed by higher energies. So they will be suppressed because you'll be looking at things at one energy scale and you'll be dividing by an energy scale which is much higher. Let's look at this in practice. I said we were looking at a single scalar field. A single scalar field has the following action, offered what we tend to call capital X, just the kinetic energy or the kinetic part of the scalar field. And so a free scalar field, you have the Einstein-Hilbert action and then the kinetic energy and the rest of matter in the universe, okay? And then effective field theory says, well, the next terms that you can add are simply functions of the scalar field times the Einstein-Hilbert term, functions of the scalar field times the kinetic energy and a potential. And the point is, any theory that you can think of with a scalar field has to include these terms unless you can come up with a reason not to include these terms, which means you have to add extra assumptions which would give you an argument to null these terms, okay? But there are symmetry arguments by which you have to do it, but it's added structure. You can add further terms, and this is where you start seeing the suppression by higher energies. You can add terms where you have the kinetic energy times box of phi, kinetic energy squared. The point is you can do this systematically. And the key thing about this is not about model building. This is if you assume that you have a scalar field and scalar field is a source of dark energy, these are the rules by which you build any theory. And if you do not want to include these terms, you have to come up with a reason not to include them. Okay? So this is completely general and it's not about model building. The next thing that works to our advantage, so there's clearly a systematic way of exploring all scalar field models using effective field theory. But there's another aspect that works very well to our advantage, which is that the scalar field varies very little in the region that we actually measure it. We only measure the evolution of the scalar field in the last few expansion times of the universe. And if you go further back in time, the scalar field is completely subdominant, so we won't probe it at all. But if you're only measuring the evolution of the scalar field in a very narrow range of its evolution, it won't have a lot of time to evolve. So it'll only vary very, very little, which means that all these free functions that appeared in the effective field theory, we can Taylor expand. In other words, we don't need to worry about these being free functions. There's just going to be we can Taylor expand and we can keep the lowest orders in the Taylor expansion. And this is an example, for example, of an axion, which is one of the models that people like to talk about, which looks like this. But if you look at how much of this potential is probed by the evolution, it's just a little bit over here, and it's beautifully fit by an inverse quadratic potential. And this is generally true. In other words, you can come up with any theory of dark energy that you want. In practice, you're only probing a little bit of it, and which means that you only need to Taylor expand whatever you're doing around a very narrow range. Well, this makes our life very easy. So let's start with quintessence, which was only dubbed quintessence in the late 90s, but which is essentially the theory that Jim proposed in 1988, which is a scalar field with a potential. And as I said, you only need to Taylor expand the potential. You don't need to worry about any other terms. Not only that, you should have a linear term here, but it turns out that if you work out the maths, you can always shift the linear term away. So you really only have these two parameters. And if you basically have two choices, you have that this m squared is positive, which means that the scalar field is rolling down here, or m squared is negative, which means the scalar field is rolling down here. All quintessence models are described like this, all of them. There's no other way of describing quintessence. They all map onto this, okay? And then you do that exercise that I gave you, which is where do the priors lie on the W0 WA plane? And you find it's quite interesting that you can now choose all the possible coupling constants to your theory, or all the possible V0 m squared, initial conditions, everything, and just map it on to where it lies on the W0 WA plane. And it lies on this thin wedge if m squared is greater than 0. If you make it general, so you have it not only like that, but like that, the wedge is a bit wider, and the data lies over here, okay? And so what you see is that actually quintessence lies outside what the data is asking for, marginally outside. These are two sigma contours, so you know it's not complete. It's not excluding it completely, but it's definitely not particularly favored by the data. All right. You can go away and do the work out what the data is saying, and just take these theories and do some inference. And what you find is indeed the data is preferring negative masses. So if it is a quintessence field, it's rolling off the top of the hill, a bit like an axion model. But the key thing you want to do is you want to work out is there any evidence for this theory given the data? So one of the things you can do is you can work out the delta chi-squared. And the delta chi-squared for the best fit quintessence model is -14, which looks pretty good. But don't forget, we've added in all these extra parameters. We've added m squared. We have to add in the initial conditions of the scalar field. So somehow you have to take into account the fact that you've added in these extra parameters to your theory, okay? And Bayesian evidence will do that. Bayesian evidence will tell you whether, will penalize with regards to these extra parameters. And so if you work out the Bayesian evidence of quintessence relative to lambda CDM, you find that it's about 3.46, which, to be honest, is not very strong. It's pretty moderate to low, okay? So there's really not very strong evidence. There's some evidence, but there's not very strong evidence the data is preferring thawing quintessence or quintessence versus lambda CDM. All right, well, let's continue with our exercise. The exercise is to use the effective field theory. What are the next terms? And the next term you would add on is a term, non-minimal coupling, which basically you have a coupling between the scalar field and the Einstein-Hilbert action, and you have a coupling constant here. And now that I'm only adding this term for consistency, I have to include a linear term in the potential, all right? So this is the next order term in the effective field theory. And if you do that, what do you find? Well, you find that you start getting equations of state which are a bit more like what the data is telling you, and this is exemplified here. You're finding that the W0 WA are lying well in the data. And if you see what this means in terms of the prior, remember this idea that you're going to see what the prior is relative to the data, you find that the prior lies bang on top of the data. It's completely consistent with the data. And so you can do inference and you can work out, and you do the inference and you find that indeed a non-minimal coupling is preferred by the data. The data is pointing that you should have non-minimal coupling. But the key thing is you want to look at the Bayesian evidence, and you do that and you find an improvement in chi-squared of -24 for the best fit, but you find a whopping massive Bayesian evidence. In other words, there's overwhelming evidence for non-minimal coupling if you want to consider, if you go down this route. So there's overwhelming evidence for non-minimal coupling. Now, you might not want to do non-minimal coupling. You might want to add in the other terms in the effective field theory, and you do that, and these are the next lowest order terms in the effective field theory, and you're going to basically find a similar thing, that they lie bang on top of the data. They lie bang on top of the data, and if you work out what the improvement in chi-squared is, it's again around 24, and you find that the Bayesian evidence is very high. So what are you finding? What you're finding is that the data is not particularly consistent with quintessence, or as bit more consistent with quintessence with the lambda CDM, but very consistent with these modifications. That, and this is kind of the summary. I'm going to ignore this wedge over here. You're finding that the data likes much more these more egregious modifications to scalar field dark energy than just quintessence. They lie over here. So the kind of the rough conclusion is if a single scalar field is the source of dark energy, then it needs something extra. It needs a potential for sure, and it either needs non-minimal coupling and broken shift symmetric. And this is true. So basically, this covers everything you might want to do with a single scalar field at low energies using effective field theory. That's it. That's all there is. And here's the rub. Both cases lead to fifth forces. What does this mean? This means the following. If you've got a scalar field and it either has non-minimal coupling or these weird effective field theory corrections to the kinetic term, it'll couple to matter as well as, it'll couple to matter in a way which is similar to gravity. And a way to think about this is we can define an effective Newtonian potential where we have the normal Newtonian potential, which satisfies the Newton-Poisson equation, and we have fluctuations in that scalar field, works as a fifth force. And it also satisfies an equation that looks like a Newton-Poisson equation, where you now have this parameter alpha, which depends on parameters of the theory. Now, geodesics will feel this effective potential. So they'll not only feel this, but they'll also feel this, which means that the modified Newton-Poisson equation will have a correction, which is a function which has this free parameter here. If it was just going to be like Newtonian gravity, this thing would be 1, but it's not. We have this correction due to the fifth force. So you go back to these theories and see what is that alpha, what is that mu? And what you find is that as a function of redshift, both of these theories deviate from normal Newtonian gravity. You have these deviations which are of order 1 away from Newtonian gravity as you come to redshift 0. So if you are going to say that these are the theory, that if a single scalar field is going to be the dark energy, then it's going to and it's going to be consistent with the expansion of the universe that we're measuring today, then you should have fifth forces. Now, we've measured fifth forces incredibly well. This is a plot produced by an ex-student of mine, Jamie Bamba, updating a plot by Adelberger, where he's taken all the latest data and he's put a constraint on that mu today, in fact, mu minus 1. And what you find is that you have incredibly tight constraints on these fifth forces. And from the previous plot, you will have seen that what we have is up here. So they're completely excluded. In principle, these dark energy models are completely excluded by constraint from fifth forces on laboratory, on astrophysical scales. It turns out it's not that simple, because one of the things that you have is, if you look at it, your effective field theory, as I said, you can add terms and you can systematically add more terms. And one of the things you find is that you can add higher order terms, and that these higher order terms introduce something called gravitational screening, specifically Weinstein screening, which suppress the fifth forces on small scales. So it is actually possible to circumvent the astrophysics and laboratory constraints by just adding more terms to the action. Another alternative is saying, look, when we look at things in astrophysics or in the laboratory, we're looking at baryons. So if we can decouple the dark energy from baryons and only couple it to dark matter, we're fine. And you can do this, and one of the ways you do this is by just coupling it to whatever dark matter particle. You only couple the dark energy to the dark matter particle, so baryons don't feel the fifth force. But both of these involve adding structure. You have to add more terms, higher order terms, or you have to futz around with the coupling between dark energy, everything. You're beginning to complicate things to get things to work. You're adding epicycles, okay? And I find this truly unsatisfactory. So the question is there any way of completely ruling these out in a way that you can't you can't bypass it with these type of tricks, these epicyclical tricks? And the two ways that you might want to do this is by looking at the integrated Sachs walks. It turns out that these screening mechanisms really don't work on very large scales. And one of the things that you can do is if you look at the cosmic microwave background, one of the terms in the cosmic microwave background measures the time variation of the gravitational potential along the line of sight to today. And in particular, it'll measure the time variation of the gravitational potential at late times. And in a paper written here by Neil Torok and Rob Crittenden, they pointed out that that time variation is positive for lambda CDM, and it would be 0 if the universe was matter-dominated. And so if you can measure the cross-correlation between this, it's called the integrated Sachs-Wolf, and a galaxy survey, you should see a positive correlation, i.e. away from 0, which is what you'd expect if the universe was matter-dominated. And there, I think, foresight was to say we can use this as a way to look for lambda. What is interesting is if you add these fifth forces, and you can't screen them, they'll lead to a negative time evolution in the gravitational potential. And so what you have here is, these are the current observations. This line here is what it is if it's lambda. And this is what it is if it's the non-minimally coupled model or the model with the dodgy kinetic terms, okay? And it's still not, the problem is that data isn't good enough to discriminate. But that would be one way to go. The question is, will the data ever be good enough to discriminate?
So, what's the quantity of
This here, it's the cross spectrum between the CMB and a galaxy survey. Okay, and if this will pick out the late time bit of the CMB of the bit that contributes late time to the CMB, which will be the integrated Sachs-Wolf. Okay. More promising is the growth rate of structure. And this is one of the targets of all the surveys that are going on at the moment. And the idea is that if you can measure the quantity I'm putting here is the growth rate of the density contrast in matter as a function of the logarithm of the scale factor. So the logarithmic growth rate of the density contrast, okay? And it's been one of the campaigns for the last 15 to 20 years to try and measure this precisely. Lambda CDM predicts this black curve over here, okay? And as you can see, if you include these fifth forces, they're going to change the way that gravitational clustering happens. They're going to change the growth rate. And so you're going to get the blue line for the one with the odd kinetic terms and the red line for the non-minimal coupling. And there have been a number of measurements, and they all lie over here with larger error bars. But I'm just going to highlight this very recent measurement, which was done by a graduate student at Oxford, Richard Stiskalek, who basically looked at 3 different data sets, supernova, Tully-Fisher data, and fundamental plane, and modeled it all really carefully and came up with this data point. And the beauty of this is at very late time. So this is basically constraints on F sigma 8 from peculiar velocities. And this is at very late times here, okay? A lot of the constraints on the growth rate are over here. So you can argue that this is decoupled, or there's no real covariance between this and the constraints on the expansion rate at higher redshifts. And this is where the curves deviate most. And what you find is it's lying bang on lambda CDM. And so it might just be that you can start to eliminate these other possibilities. Well, it's wishful thinking. So I asked one of my colleagues to do the following, to first of all, just do a run with that data point, that measurement F sigma 8, no expansion rate. And remember that I said that if you just use the expansion rate, you get a non-zero detection of this non-minimal coupling parameter over here. If you do an analysis only with F sigma 8, it's consistent with 0, but it still has a broad support out to here, okay? And another odd way to look at this, but I find it quite useful, is remember that we have the data over here. Now imagine that I take the non-minimal theory and just constrain it with F sigma 8 and then find what the corresponding W0 WA would be for those models. It lies over here. So it's centered on lambda, but the data is not yet sufficiently constraining to be completely inconsistent with this, okay? The hope is that the data will improve and that at some point you will find that the F sigma 8 is completely inconsistent with what you're getting with DESI, which means that this theory, non-minimally coupled theories simply don't work. So what does the future hold? This is the situation today, okay? And this is why my conclusions are flabby and will accept changes in how we might interpret the data. Remember that this is the quintessence wedge, and this is the more general dark energy where you have to either have non-minimal coupling or modifications to the kinetic term. Now, what might happen is that that data will improve, and corrections will be such that in the next 3 years, the contours will lie over here. And one point I want to make is this is the uncertainties that we will get on W0, WA by the time we finish stage 4. It's better, but it's not incredible, all right? So we are, in some sense, we are already in the stage 4 era with these current constraints. But if it moves over to here, it's back to being consistent with lambda CDM. But it's also consistent with quintessence, which means that basically it could be lambda CDM, it could be quintessence. And as I've said, all you need to describe quintessence is really a mean and a mass squared. And so you'll be complete, you can describe everything, all possible theories which are consistent with the data in terms of these two parameters, and that's it. So there'll be still a great underdetermination. If we go back to the theoretical sludge, all those models will have to map onto this, okay? The other possibility is that this thing migrates a bit upwards, okay? And then you'd probably eliminate lambda CDM, but then you'd map onto quintessence, thawing quintessence, and again, you'd only need 2 parameters to describe it. All those trillions of models, all you need is something which is described in this way. More interesting is if the data holds up and this starts to migrate downwards, right? Well, then it couldn't be lambda, it couldn't be thawing quintessence. Then you start to have to describe it, if it's a scalar field model, in terms of a ton of parameters, because you want to screen, you want to be able to screen what's going on astrophysical scales. So it becomes a kind of epicyclical model of dark energy. But what if then a measurement of F sigma 8 is such that it completely eliminates those models? Then no scalar field theory of dark energy, no single scalar field theory of dark energy can be used to explain dark energy. And we have to start thinking afresh of what might be the explanation for the expansion, for the accelerated expansion rate of the universe. So the conclusions that I have, and then I'll end with a thought, is that I think, as I said, constraints are still in a state of flux for the reasons that I gave you, okay? And the thing that I also wanted to drive home is do not overinterpret the meaning of W0, WA. They're just compression parameters. They're just ways of condensing the data. The thing that I would say is do not add to the sludge, right? Don't make up models. There's just no point in doing that, right? There's really no point in doing that. Stick to EFT, because EFT basically describes what dark energy, scalar field dark energy does at those energy scales. More specifically, what is the data currently saying, if we believe the data, is that lambda is marginally disfavored, but it depends on assumptions, as I mentioned. That quintessence is marginally favored over lambda, but by very little. I think it's scant evidence. That non-minimal and broken shift symmetric, which basically covers everything else beyond that, is greatly favored, but it's grossly inconsistent with gravitational constraints from astrophysics and laboratories. You can bypass these by using higher order terms to introduce gravitational screening, or by violating the weak equivalence principle by coupling dark energy only to dark matter. But I see this as very much as epicyclic, and my concern with that is you go back into the worry that Withrow was throwing at Bondi, which is you end up discussing opinions. Which one is the better theory? Which is the more elegant? It's just not a very satisfying situation. It may be that future measurements of the growth rate will just wipe the slate clean and get rid of these theories. Depending on future data, I think it's fair to say that there will be complete underdetermination in terms of if we either have complete underdetermination, if we end up in the lambda cosmological constant part of the plot, or in the thawing quintessence, or the Ptolemaic era, as I call it, because models have become so complicated, or something else. We need to think about something else. And the thing that I want to finish off by saying, and it's good that I'm doing this at Princeton, is in 1907, Einstein wrote a paper explaining Brownian motion, right? And Brownian motion, you've got these bits of pollen propagating through water in a zigzag. And he came up, he developed the statistical theory of liquids, and he was able to use the motions of the pollen grains to infer something about the molecular structure of water. He was able to figure out the sizes, the mean velocities of the molecules. He was able to say something about some level of microphysics about the water. But he was not able, and he would never be able to say anything about molecular structure or atomic structure. There's no way from those observations that he would say something truly meaningful about the microphysics of water. And you might argue, and the only way you could do that is through spectroscopy. Is you have to have a different type of data to say something about what is actually going on. You might say the same thing about cosmology, that cosmology will never really be able to tell you what is the microphysics of dark energy in a precise way. It can just tell you some rough microphysical statements about m squared, a lambda or something, but it won't really tell you what is the true underlying theory. And to do that, you would need something equivalent to spectroscopy for dark energy, which, in all honesty, I have no idea what that is. And I think I'll end here.
Thanks for this nice talk. I'm wondering, for these models with non-minimal coupling, something that might happen is, for example, you change the propagation properties of the graviton. Are these folded into account in the priors and double unclear that you get?
Please don't change the propagation to graviton, no.
Are there other sort of fundamental theoretical constraints that you can impose to narrow down the priors?
I'm avoiding light to play theoretical constraints. The problem that I found is that theoretical constraints, you enter the world of opinion. Some people think you need to apply this, other people. And so that's, I want to do this as much data-driven as possible.
The other hypothetical component is dark matter. I'm wondering if you could reduce the number of epicycles in the dark energy component by putting one of the two of them into the dark matter. The dark matter now, as it now is vision, was introduced in the 1980s to be the simplest thing you can get away with. Yes. Surely there's a better theory than that.
That's true. I mean, and the thing about dark matter is there are other ways of probing it, not just cosmological, but possibly. But I think that's for theorists to think about.
So in the Daisy paper, there was a plot where they showed W as a function of redshift, and it was less than -1 at some point. So
which plot are you talking about?
W is a function of redshift in the Daisy paper, or in your slides. I don't think I've seen it in your slides.
Is it this one?
Oh yeah, okay.
I kind of avoided showing plots of W as a function of redshift.
So anyway, my question is, can I see your finding that these non-minimal models are favored as simply the requirement that minimal models will never achieve a phantom equational state? So you need to take it, to have some minimal.
So here's my problem is you write down the non-minimal theory, okay? So when you talk about the equation of state, you're talking about P over rho, right? And so you think of it as the standard Friedmann equation where you have something plus something with that equation of state, right? Now, if you look at the non-minimal theory, it doesn't look like that at all. So we can rearrange everything in the evolution equations in such a way that it looks like it has something with an equation of state, but it makes no sense because there's nothing there which is the equation of state of a pressure and an energy. And this is why I go on and on about when we measure W naught W, it's just a way of compressing something if we assume a model for the Friedmann equations. But we know that in both of those cases that I held, the Friedmann equations don't look like that. And that's why I do not plot equations of state. But minimals, yes.
And so my question is, your finding is simply that it must be above the line where W is always larger than -1. So your contours look a lot like that.
Sorry, I misheard you. You're saying you're only talking about minimal theories.
Well, you said that minimal theories are disfavored compared to non-minimal ones because of this.
Yes.
And I'm saying that this looks a lot like simply the requirement that you don't get phantom.
It could be, but again, that plot, that wedge, looks different if I'd used a different data set. That's the key point, is you have to pick a data set with certain parameters, and the wedge looks like that for that. If I'd only done this, for example, for DESI, that wedge would have looked different. If I'd done it another way, it would have looked different. Yeah.
Perhaps a way around some of the confusion of equations of state and our ability to measure it would be to just measure the energy density of dark energy as a function of redshift. You showed this plot near the beginning where your W is changing with redshift and how you fit different W naught WAs depending on what redshift range your experiment is sensitive to. Do you have any suggestion if we switch to reporting and measuring dark energy density as a function of redshift?
So my whole thing is, that's just another way of parametrizing. But if you think of what I was saying, our colleague over here, that's true if the universe satisfies the Friedmann equation, right? But if you have non-minimal coupling, what do you call this energy? What is this energy density, right? So you could do that. You could find that there's a better way. Personally, I don't think it makes any difference. But you shouldn't assign it the meaning of the energy density, because if you look at, for example, the non-minimal theory, it doesn't divide up in that simply into an energy density for the dark energy and everything else.
And then we'll have Nadia. I have a simple question. How does the Hubble tension, where we see the Hubble constant changing or uncertain with redshift, because all of that depends on H of A.
Very good. I didn't include any low H local H measurements. And again, I'm going to invoke the Eustathiou argument, which is I'm going to park the Hubble tension for this talk. But it plays a role. If we include it, things might change. Yes. Yeah.
I have a question about the sigma A's that you showed towards the end. So you have these pink and blue regions that now deviate from the observed point. But you also said that thank you. But those pink and blue regions previously were very strongly constrained by the fifth force. Has this already been propagated here, or those two orthogonal constraints, or?
So the point is, these screening mechanisms, they work very much locally, so you have to look at very large scale measurements. And so the hope is if you're constraining something on sufficiently large scales, it hasn't been affected by the screening. So you might have these gravitational screening terms which protect things, but they wouldn't affect this.
Exactly on the house, so let's carry on the conversation. Lunch, thank Pedro.